In this short video, I will discuss the attempt to use principal component analysis to provide independent variables for multiple regression model. I did that for two sets of data. Both were used before in our course. The first one is the data about life expectancy. We predict based on a bunch of health, economic and sociological variables. We can more or less refresh our memory about what variables we have in our disposal. So there is the potential dependent variable life expectancy expressed in years. And we have the following variables, some of them medical. So medical variables are, for example, number of measles cases per 1,000 people in population, or immunization against different diseases. This includes polio, DTP free. There is also data about deaths due to HIV in children under 4 years. There are probably also medical data is thinness in children and thinness in young people. There are sociological data like human development index, like number of years of schooling. There are, say, demographic data as adult mortality or mortality in infants, number of infants deaths, as well as mortality among children. And there are also economic data like GDP per capita or government expenditure on health. So there are very different variables, and what we are going to do, we are going to find principal components and check whether they are good sources of predictors for life expectancy in years. Since all our variables are in very different units and have very different scales, we will definitely try to standardize the variables. First, we look at the total correlation matrix. So we've seen this picture before. There are variables that are very highly correlated. Here is those two variables, which is human development index and years of schooling. Schooling are very highly correlated with our dependent variable. Okay, but now we will not be taking into account the first row, but rather we will work on the rest on the matrix. So we exclude the dependent variable and we work on 17 independent variables, and now I will not be selecting variables initially. I just work on the full size. And as I said, first I standardize the variables and then I calculate a correlation matrix for the standardized variable, which is of course the same as a correlation matrix of original variables. We look for eigenvalues and eigenvectors, and what we get is the following table of eigenvalues. as we can see, there are several eigenvalues which are quite large. And the decrease is gradual. It's slow. When we look at the plot that we used before, with the eigenvalues of consecutive principal components, we don't really see the clear point when we should stop when we should stop taking components into account. Yeah, it is really very gradual. The same when we look at the cumulative percentage of total variance that the components contain. So the first component contains a little bit less than 0.5 or 0.4 of the whole variance, and then 1, 2, 3, 4, 5, 6. Really, when we want to have something like 0.8 of the total variance as we had in the previous example, we will have to take into account like 6 components, which is a large number if we think of if we think of the regression model. So let us now look how principal components correlate linearly with our independent variable, and these are plots. As you can see, the first 2 components have more or less linear dependence with the life expectancy, while other I'll produce hazy halo of points, so there is no clear linear dependence here. We can check how what R-square we get while using different subsets of principal components to as predictors for our multiple regression model. And let us start with first 2 components. With first 2 components, we really don't have a very big R-square compared with what we got previously while predicting using original variables. So with first 2 components only we have 0.69 probably if we round up correctly. So almost 0.7. Maybe we can also do it for one component, for the first component only. It doesn't work. Sorry, something is wrong. Maybe yeah, okay, it should be sorry, so it should be with no, so this was probably this previous one was probably with the first component. Yes, because our dependent variable is the first one, and yeah, so here should be, sorry. Yeah, okay, so sorry, so this number that we got here is in fact R squared when we use only one principal component, the first one. Sorry, I mixed up a little bit earlier. And then we add the second component, the second principal component to the mix. Yes, and what we get is considerable increase. So there is almost 3/4 now. And we can check how it gets better. It should get better when we add other components. So the fourth one a little bit increased, and the fifth one, the last one that I have calculated, so 0.82. So finally we get quite high R square. However, the model now with 4 independent variables is rather complicated, so it won't be probably practical to use it. Maybe I can add one more. Yeah, I can add one more, but nothing much happens. So no use of doing that. Okay, so let us then see what are the loadings of our components, all 5 of them, and probably maybe I will copy them to some more manageable format or like that, and let us look for high correlations. So here I have variables, and here I have principal components in order of decreasing eigenvalue, and I want to look for high correlation. So here is definitely something that I would call high correlation. Let us mark correlation above 1/2. And here is above, and here is, I mean, negative is also okay as long as it is big. Here we have something serious, and these are serious. This is serious. This is also above 1/2, and here we have above 1/2. In the third component, this is high correlation, this is high correlation, this is high correlation, and this is high correlation. Yes, and that's all. Then for the fourth component, this is high, and this is high, and this is high. What more, for the fifth component, those loadings are not, oh, this is a series correlation, and the rest is not that important, and this is also series correlation. Okay, so when we look at these components, we can see that I suppose the first component should be considered a component that contains mostly sociological data. We have here BMI, which is correlated probably with a lifestyle. The number of years of schooling and this human development index, they are sociological data and adult mortality. It may be considered health data, but also probably it is somehow correlated with sociological factors like lifestyle. So this first component I will consider to be responsible for sociological components, sociological factors. Then the second components, let us look what happens here. There are the same variables, the same last 2 variables, and there is also a considerable input from thinness, and there are all those information about mortality here also. No, I must admit that I cannot really interpret this clearly. And there is the third component. We have infant mortality, we have measles cases, we have children deaths, and there is also expenditure on health. So I will say this is the component that says something about health of children in general. It is positively correlated with infant mortality, with measles cases, and with children death. So the bigger this principal component, the worse health of children in a country is. And the fourth component, hepatitis B, polio, and DTP. So this component is definitely about vaccination. Yeah. Yeah, and I think that's all what I would like to say about interpretation of these components. So, as a source of independent variables for principal as a source of independent variables for multiple regression, probably it is not the best choice, because to obtain high R square, here we had to use like 5 independent variables, but the interpretation of those principal components becomes quite interesting, especially this component that says something about health of children, and PC4 that says something about vaccination. It seems that this principal component analysis really captured kind of groups of variables that appear in this data set. It might be interesting, from this point of view, it might be interesting to use them as input for factor analysis. That will be the subject of our next lecture. Okay, so now let us change the topic. Not the topic, but the example. Now we again look for principal components as inputs for multiple regression variables, but now we work with our fuel consumption data. So we have again 11 variables. First is fuel consumption, which is our dependent variable, and a bunch of technical data and performance data of cars. Again, those potential independent variables are in very different scales and units. Therefore, what we are going to do is to standardize them. We do the standardization, and then we look at the heat map of the correlation matrix. This is now only potential independent variable, so this x1 variable about fuel consumption is excluded from this matrix, and we see that there are variables that are highly clusters of variables that are highly correlated. These first 3 are highly correlated between themselves, and 9 and 10 are also highly correlated between themselves. Probably this heading row is not very useful here because the sizes are wrong. Okay. So then we do what we did before. We calculate eigenvalues and eigenvectors of the correlation matrix, and what we see is that the 2 first principal components have the highest eigenvalues, which are variances of the components, and we also can see on the plot that using that from the plot, and using this rule that when the plot changes, we should stop. It means that we should use first 3 principal components. However, if we look at the percentage of variance that is taken into account, we see that already 2 first component have above 0.84% of variance. When we add here the third, what we will see, yeah, this is that. Yeah, so this is 90% of variance. So either 2 or 3 principal components should be used. We can decide later. And let us look what happens. We calculate our factors. And we look of regression models with 1, 2, and 3 principal components. And when we see, and here are the numbers. So regression model with the first principal component gives us R squared on the level of 0.82, 83 if rounded properly. This almost the same with the first and the second component, but when we add the third component, R squared goes up to 0.85. So the decision is clear here. Either we use only the first component or we use the 3 of them. Yeah, we could maybe see what happens if we forget the third, if we forget which one? The second. Yes, the second is not really that great. So let us forget the second. 3, 4. 3, 4. What happens? Yeah, so already 853. So we can maybe forget just the second. Use the 2 of them and forget the second. The first and the third. Let us look at loadings. So what is the what are the interpretation of those components? So the first one has high input from roughly everything. So it is just the whole bunch of data combined together. And the second principal component has those 3 last variables. I've already forgotten what are they. The type of transmission, number of forward gears, and number of carburetors. So these are definitely technical data, construction of our that contain information about construction of our car. And there is X7. What's X7? X7 is quarter of mile time in seconds. Yeah, so this is the performance variable. And there is this third component here. It does not have correlation above 0.5, but still it is the highest correlation from all those component, all variables. And it seems that from the point of view of our prediction, this component is important, because when we used just the first and the third principal component, we got what we wanted, quite high R square, with only 2 variables being predictors. However, interpretation of those variables now is not that clear. For comparison, when we selected variables for multiple regression model from among original variables using one of our selection procedures, we got R squared on the level 0.84. So this is a little bit better when we use this principal components as inputs, but there is no really clear interpretation. So if we want only just good quality prediction, it is worth doing it. If we have if we want a prediction together with some interpretation, probably we should stick with original data. Okay, so that's all for now.